Okay, this is part 23 of Prevent and Reverse Afib and Congestive Heart Failure by me, Pete Rogers. We've been talking about hypertension. We're on page 118. We're starting now on the windkessel effect. The windkessel effect means that the ascending thoracic aorta has a lot of elastic fibers. So when the heart pumps blood into the ascending thoracic aorta, it's stretched outward by that influx of blood. And then when the heart relaxes, heart relaxation is called diastole. Heart contraction is called systole. So when the heart relaxes, the elastic fibers of the ascending thoracic aorta, they have elastic recoil. They pull inward, and that pushes blood during diastole. So that's diastolic flow, the lower number of blood pressure. And the point of this all is that chronic overstretching of those fibers by chronic hypertension for decades destroys those elastic fibers. And the weaker those elastic fibers get, the less diastolic flow can be generated. As you lose the ability to generate diastolic flow, then you have to have increased systolic flow, meaning harder cardiac contraction. Chronic increased cardiac contraction of the left ventricle leads to left ventricular hypertrophy, thickening of the musculature. Now, thickened musculature is going to be it's going to take more effort to perfuse it with an adequate amount of blood. So you can get yourself into a vicious cycle where the left ventricle is contracting longer, harder, stronger, and it needs more blood, but now it's harder to get blood into it because the left ventricle muscle fills with blood when it's relaxed during diastole. You see the vicious cycle risk there? All right, so anyways, it's after people get destruction of their windkessel effect that they start having more and more systolic hypertension, and then now their blood has to be pumped at a higher pressure because again the goal is to get adequate amount of blood to your cerebral cortex, the top of your brain, and if you have less diastolic flow, then you're going to need to pump more flow during systole. The higher the pressure, the higher the velocity of the systolic flow, the harder it's going to bang against the walls of your arteries, especially at bifurcations. And that higher pressure on a chronic basis is going to damage the arteries and cause atherosclerosis. The two biggest risk factors for atherosclerosis are high-fat diets, associated with high LDL cholesterol, and hypertension. Okay, so let's go here. Okay, this next picture here is going to show, sorry about that picture moving along. I'm just going to show you what endothelial cells look like in this drawing. They're basically spindle-shaped and they're orientated with their long axis along the direction of flow. And they have little cilia-like projections from them, little proteins that can sense the direction of flow. So normally flow should be predominantly going in this direction along their long axis, and the flow should be what is called laminar. So laminar flow has a parabolic velocity profile like that. And the red blood cells are in the center. That would be like my two middle fingers. Then the index finger and the pinky would be like the white blood cells. And then the plasma, like my thumbs there. And that's right alongside the side of the vessel. So that's called laminar flow. When you've got high-fat diets or something else causing the red blood cells to stick together, sticking together red blood cells is called rouleau formation, stack of coins. It's also often referred to as blood sludge. Anyways, the higher pressure, though, I'll show you what's going to happen on the next slide, how it's going to cause problems. So basically, if you're pumping thin blood like water, you can pump at a lower pressure. If you're pumping thick blood, you got to pump a higher pressure to get it up to the top of your brain. And then it's worse, too, if you have a lot of dietary sodium constricting the vessels, vasoconstriction, vasovessel constriction to narrow. Then you're pumping thick blood through a narrow system, pressure has to go up more. So what happens is the elevated systolic blood pressure means elevated systolic velocity of that blood. So it's going to come up here to the junction of the common carotid artery in the neck. You can think of it as being like a hand. The thumb goes up into the skull. That's the internal carotid artery, goes up into the brain. The fingers are like external carotid artery branches. Those go to the face. All right, so the internal carotid is the important one. So when this blood comes up to the common carotid, hits the bifurcation, the median divider, so to speak, you get an excessive amount of turbulent flow because of the high velocity of the hypertension, high systolic pressure blood. So turbulent flow means chaotic flow that bounces off of it. You'll also get increased retrograde flow, which means backwards flow. And the retrograde backwards flow is when it's in excessive amounts, it's sensed by the arterial lining cells of the internal carotid artery here on the wall far away from the median divider or the bifurcation. It'll sense that as abnormal. If there's too much turbulent flow, too much backwards flow. And it'll start to shed its antithrombotic glycocalyx. The mnemonic for the glycocalyx, the coating on the arterial wall, the endothelium is also the name of the arterial wall cells, is 666. So 6 for 600 nanometers is the height of the antithrombotic glycocalyx with a zeta potential, meaning a negative charge, full of negatively charged glycosaminoglycans from heparin sulfates, also from sialic acids at the end, from cholesterol sulfate. So anyways, negative charge zeta potential, which repels the negatively charged red blood cells. But with excessive turbulent flow, excessive retrograde eddy currents, that antithrombotic glycocalyx is shed, and now sitting beneath it are the adhesive molecules, things like VCAM, vascular cell adhesive molecule. That's what the mnemonic 666 comes from. 600 for 600 nanometers, the big high antithrombotic glycocalyx. When that's shed, sitting below it is 60 nanometers in height, vascular cell adhesion molecule protein. And below that is the plasma membrane, which is about 6 nanometers. Okay, so that's how you remember 666. The first 6 for 600 for the antithrombotic glycocalyx, then the 60 for the prothrombotic adhesive proteins that normally are hidden by the glycocalyx, and then 6 for the thickness of the plasma membrane afterwards. So anyways, you don't want this. Hypertension is bad. Okay, and if you got it, you don't want to make it worse. Okay, and I see this every day. That's where you always get the clot forming. Atherosclerosis is a blood clot. This is where it always forms, on the side opposite the bifurcation. I see that all day long, every day. Okay. All right, so the point of that was to avoid high-fat diets. I'll go a little bit through the electrolytes today. I'll cover a little bit more material. So normally, you have a plasma membrane in your cells. In a regular cell, this might be about 30% of the energy goes to run this ATP pump for this potassium sodium ATP pump. You can often call it the sodium potassium ATPase or potassium sodium ATPase. K is for kalium for potassium, N is for natrium for sodium, the Latin version of the word. It's normally going to be bringing in 2 potassiums and pumping out 3 sodiums. So there's a net outward positive charge. More charge is being pumped out than is coming in. So that means you have an electrical current, okay? That makes the inside of the cell slightly negatively charged, negative 65 millivolts. Okay, that's going to create a gradient both of charge, because you're going to have 10 times as much sodium outside the cell than inside the cell. So that's a concentration gradient. You're going to have negative charge inside the cell. That's an electrical gradient. So you have an electrical chemical gradient. And the entry of sodium then, because it wants to come into the cell, it's attracted to equalize its concentration gradient of the element itself, and because it's attracted to the negative charge, well, that attraction of the sodium, which I've described as, the angry poor trying to bust in, can be coupled to pumping calcium out. And that's how normal cells function. Also, if you eat too much dietary sodium, not enough potassium, you will start to dissipate this gradient, and you'll get more sodium inside the cell, because there's a fixed amount always of how much positive charge is inside the cell. The main inside intracellular cations are potassium and sodium, and they're about 98% of the positive charge inside a cell. And so you want to keep that how it is. If you accumulate more sodium in the cell, you're going to lose potassium. And then you're also going to void it out when you excrete in your urine. You don't want that, because that's going to decrease your ability to run the sodium potassium ATPase. It's going to dissipate your gradient here, which means it's going to decrease your ability to pump this calcium out. Trust me, that's a big deal, because everything in the cell is based on handling this calcium. That sodium potassium ATP pump is like the electrical battery of the cell. Okay, here's a great book if you want to understand ion pumps more. This is a really good book. Richard Moore's High Blood Pressure Solution, MD, PhD guy. He spent about his entire adult career working on these pumps in the context of understanding hypertension. I think my video that I made about making up metaphors for the ions is really helpful. So you should watch that if you want to understand the stuff better. I called that video Membrane Ion Pumps with Metaphors, and I basically called sodium the angry poor trying to bust into the cell. Potassium, dear old dad, the good guy, middle class worker trying to make things work. I called magnesium the heroic ion, because it keeps the phosphates in place, the second and third phosphate on ATP, so they don't prematurely separate, so you can run that ATP pump effectively. It also does other beneficial things. And you get magnesium. It's located in the center of chlorophyll. So if you want to get magnesium, just eat your plant foods. There it is. It's in the center of chlorophyll. So you eat your plant foods, you get your magnesium. Inside the cell is tons of potassium. So you eat your whole plant foods, you get your potassium. Okay? And they're low in sodium. That's what you want. Versus when you eat processed food, it's high in sodium. and it's very low in potassium and magnesium. So that's bad. That will mess up your metabolism long term. And I can tell you, Richard Morris said it. He said, you can't get around this. You either eat the adequate amounts of potassium relative to sodium, or you're going to have decreased cell function. There's no way around that. You can't just take a pill and avoid that problem. Okay, so he calls the K factor the ratio of potassium to sodium. And at a minimum, you could have it at 5. Meat's about 4. Okay, we went through this though, but fruits are about 100 to 500 times more potassium than sodium. Starches are about 20 to 100 times more potassium than sodium. Veggies are about 5 to 20 times more potassium than sodium. So all the plant foods are good. Fruits are the best in that sense for K factor. Starches are very good. But what you don't want is be eating these processed foods, because they tend to be very high in sodium and very low in potassium. Because what they do is they grind them up, and when they grind them up, they rinse them with water and solvents, and they rinse away all the potassium. And then they add sodium back for flavor and as a preservative. So they tend to be real high in sodium, what you absolutely don't want. And then low in the good thing that you want is the potassium. Okay. And like I said, to maintain the membrane osmolality, you have to have a constant amount of positively charged ions inside the cell. That's called and they're called cations, positively charged ions. You can remember cat purrs, P for positive ions inside the cell. So you can't change this ratio, so that if you eat excessive dietary sodium, you're going to dissipate these gradients. You're going to have decreased cellular function. You can't have an increased amount of positive ions in the cell, because the water would follow it, the charge, and then the cell would overflow and burst if it was hyperosmolar. So you can't just like pack more in there. It won't happen. Actually, I think we'll leave it there for this time, and next time we'll come back, we'll explain a little more detail about these ion pumps. I hope you found that helpful.